Okay. So last class, we learned about how to use OpenCV. Okay, and I promised to show you some demo in the Colab environment. So I will start that from now on. So first, in the last lecture note, you can find this link, actually, the Colab link. So, I mean, you have to follow that. You have to put that link in the browser, then you can actually could go here, the Colab. And you also have to register to the Gmail. You have to have the Gmail account to use this Colab environment. And also, you can download the image and also the video files. Anyways, the files you require, you can download from this link. Okay, you actually need 2 image files and also 1 video file. So if you follow this link, then you can download those files. And I already downloaded that. And also, actually, this is the link. Okay, in that link, you can find 4 files actually. So this is the first one is the example.avi, which is the video, and the second one is the example.jpg, and also the third one is example4.jpg. Those are 2 images capturing the Unis campus, and also fourth is the OpenCV.ipynb file, which is actually the binary file which saves all the code here. Okay, so I mean, if you want to reproduce this practice in the Colab, then you can actually upload this ipynb file. You can actually, maybe for foreigners, you cannot read this. So this is some file menu. And here it is saying we want to open the ipynb file. Okay, so if you, and also here it is saying that we can upload that ipynb file. So actually you can select this upload node. And if you select this file, OpenCV.ipynb file, then you can get this environment, the same environment as me. Okay, so you can get this environment. And next thing you have to do is, this is saying visualize the file browser. So click this. Then it needs time to connect to the file system. And the thing you have to do is click this, then you can actually select 3 files you downloaded, and then it is uploaded in this Colab environment. Okay, then you can access these 3 files with the path like this, /content/example.jpg. So in the first code, you can see such a path. Okay, so the first code is the code for reading the images, but not sure why it is not. Okay. Okay. Yeah, it is executed now. Maybe. Okay. So I think the code is deleted. Anyways, Yeah, first, at first time, this flag was set as unchanged. And then if you read the JPEG file, then you can read the original image contained in this example.jpg. But if you change the flags, then it can read different mode. And previously it was set to read the grayscale image. So if you change it like this and read the image, then the IMG, this variable will have the images which is load in the grayscale. Okay. So I mean, the CV2, this is OpenCV. This is the code, import CV2. This is the code to import the OpenCV library in the Colab environment. And also the thing you have to do to read the images is only write down this code, cv2.imread. And you have to specify where the images are. And you also have to have one flag, okay? So you can set this as the unchanged to read the original image, okay? Or you can change it to something else to give some, give some flag, okay? And this is the CV2_im show. This is the code for visualizing the loaded image. So anyway, this img variable is having the image information, the loaded image information. So yeah, if you execute this, you can see this image. This is the images contained in the example.jpg. Okay. Okay, and now you can see, you can access the image variable as if it is the arrays in the maybe the Python. Okay, so if you visualize its shape, then you can see this. Okay, it is meaning that it has three channels, which is the R channel, which denote the red channel, G channel, green channel, and B channel, blue channel. So the RGB images are constituted with the three channels, which is RGB. And also this is denoting width, and this is denoting the height of the image. Okay, everyone following this? Okay. It's easy, right? So if you use the OpenCV, reading images become very easy. Okay, and also you can access the pixel values. So you can access the left topmost pixels RGB value by printing out this variable. Okay, so you can use img variable as the standard arrays in the Python. Okay, so but remember that this is not RGB, but the order is BGR. Okay, so blue value is 182 and green is 115 and the red is 0. Okay, for this pixel. So this is the pixel located here, right? And you can also access the channel as well. So if you access the blue channel value for this pixel, then you can do this, okay? And you can see that value is 182. Okay, and also you can visualize. This is the grammar in Python selecting all. This is meaning that selecting all the pixels in the first dimension and also selecting all the dimension in the second dimension and select only the first in the third dimension. So it is showing only the blue channel of the image. Okay, so everyone understanding this? Okay. So I mean, previously when you read the image, you did was if you delete this, then you visualize the original image. But what they do here is they want to visualize only the blue channel, okay? And if you change this to 1, then it is visualizing only the green channel. And this will visualize the red channel. Okay. And also, I mentioned that if you use the OpenCV, you can do everything that Photoshop is doing. Okay. So I will show you the examples here. So you can, if you read the images first, and you save your image in this img variable, and in that image variable, you can draw some rectangles with some, I mean, whose the color is changed. So this part is denoting the thickness of the rectangle, their line, and this is denoting their color. Okay, and this is denoting the starting point, location, XY coordinate, and end coordinate. Okay, so anyways, this is the function that can draw some rectangles in the images. And after that, if you visualize the image again, then you can see this kind of image. Okay, and also you can draw some polylines. So here, the thing you have to do is define some point here, 50 by 50, maybe that would be the pixel in this location, and 150, 150, that is the, the location here, and 100, 140, that is some location here, right? And 200, 240, that's the location here. You have to define some point, their pixel locations, and using these polylines, you can draw some polylines like this, okay? And if you visualize image again, then this line is added in the original image, okay? Okay. And you can also draw some circle and ellipse. So I will omit the detailed usage for these functions, but anyways, you need this image variable and some parameters for drawing the circle, okay? And also you can also put some text on the image variable, okay? You can modify their font, their size, and also their color and their locations, okay? So, yeah. And maybe if I change this to maybe this, then the color will be changed to red. Okay, like this. And also you can resize the images, okay, using the CV2 resize function. So the usage for this function is very simple. Okay. And also you can apply some blur filter on the loaded image. So, I mean, this CV2.blur, that is the function for making images blurred. So if you change these parameters, then the images are blurred. And if you change these parameters, then you can see the blur is less, become less, okay? So you can, anyways, do this kind of image blurring in the OpenCV with the one line of code. And also, you can also detect some edges, the edge component of the images, okay? That is also can be done using just one line of code, okay? And also you can change their parameters like this. Then the obtained edge detected result becomes slightly changed. Okay. And also, this is the corner detection algorithm, which is very famous actually, whose name is Harris corner detection algorithm. And yeah, actually you can detect corner, their locations with this one line of code implemented in OpenCV, and the other codes are for actually visualizing that code locations. So this is for visualizing code with red circles, okay? So, I mean, the code is defined as the point, the horizontal and vertical component are meeting. So this point are some corner in this image, okay? And also this is another complex algorithm, but already implemented in OpenCV. So what they do is image matching. So given two images, which is different, but capturing the same object, in the image matching, what you have to do is match the same object pixels. Okay, this is very hard problem, but in OpenCV, you can implement that using 3 lines of code. Okay, so I just want to show that OpenCV makes everything simple. Okay, you don't have to remember, or I mean, I don't mean you can implement everything by yourself for this kind of thing, but I want to say that the OpenCV that is making image processing very easy. Okay. And another thing is, I showed you how to read the images in OpenCV. So you can just use this cv2.imread function for that, okay? But if you want to write the images, then the thing you can do is just specify where to save, okay? The location and the file name you want to save. And then the image variable, which contains the image information. This IMWrite needs these 2 arguments, and just by inputting these 2 arguments into the IMWrite function, then you can see if you refresh this folder, then example2.jpg is created. So, and also maybe if you change this to make new image files in the PNG format, then you can also see so PNG example2.jpg 2.png is created. Okay, so OpenCV automatically deal with this image formatting. Okay. And also, the last thing I want to show you is if you want to read the video files, which is in the AVI format, the thing you have to do is you can use the cv2.video capture function and make some file descriptor here. And if you call this cap.read once, then this each frames, video is constituted with multiple frames. If you call this cap.read once, then one frame is, earlier frames are read. So you can visualize that one by one. So, and also this return value is indicating that that frame is the last frame or not. Okay. So if you loop this cap.read until this return value is false, then you can read all the frames contained in the video. Okay, so that's happening here. Okay, so this is all the experiment for the OpenCV library. So I want to say that this OpenCV is the open library. Okay, open source library. So actually, it is still expanding. Okay, so it is still expanding. So I cannot deal with every functions they are containing because they are still expanding. But if you go to the OpenCV website, then they are providing manuals for how to use their functions. And also, they are providing some examples for usage. So you can refer them and have to choose which function you have to use for implementing your own project, okay? So this is all for OpenCV. So are you guys following this? Okay, maybe not that difficult. And the thing next thing is so I will I will start the second lecture, the review on deep learning. But I'm missing how to, okay. Strange. Okay, this one, I need this. Okay. So today we will start the second lecture, which is the review on deep learning. Okay. So I already showed you this slide, the ImageNet challenge. Okay. So this is the largest data set, the ImageNet, that was the largest benchmark, which is developed for image classification task. Okay. It has 1,000 object classes, and also images, they are having this number of training and testing images, which is very large in scale. And the thing you have to do is you have to make some AI algorithm that can classify this individual, these individual images, which contain just one main object. And the thing you have to do is classify, reveal the main object inside the images, okay? And this is kind of the probability for 1,000 objects. So, it estimates the probability for 1,000 objects, and the one that have the largest probability is selected as actually they are predicted as the main object for these images, okay? And also we have to compare that predicted images, predicted classes with the ground truth classes, and actually find that image is correct or not, okay? Correctly classified by AI algorithm or not, okay? And we can measure their accuracy. And this is also the tables I showed you last class. And this is the year, the x-axis, that's the year, and the x-axis, that's showing the error rate. Okay, this is actually 100% minus accuracy. Okay, so error rate is denoting given 100 image, how many images will be incorrectly estimated by the AI model. Okay. So this error rate indicates the better AI model if their value is becoming lower, okay? As years go, this error rate becomes lower, okay? But you have to remember these 2 years. In the year of 2012, firstly, the deep learning algorithm having 8 layers, whose name is AlexNet, appeared in NIPS conference, and they actually reduced the error rate by almost 10%. Okay. Here, at the year of 2011, people thought machine learning is almost over, so they cannot improve, beyond this 25% error rate. So only a small amount of gain was appeared using previous SVM or random forest, when using such shallow layered algorithm, we can see only small amount of gain compared to the state of the art. But at the year of 2012, the deep learning algorithm having L layers appeared, and they achieved actually 10% gain. Okay, so after this, people are getting interested in deep learning algorithms again. This is very important event. And at the year of 2015, the deep learning algorithm having 152 layers appeared, and they are actually surpassing the human evaluation performance in image classification task. Okay, even humans fail for 5 images when given 100 images for image classification task that is indicated here, right? But when using ResNet architecture, having very large, very deep architecture, their error rate becomes 3.6%, okay, which is better than the human performance, okay? So these two are very sensational events, okay? And after that, people are using deep learning approaches for solving many, many computer vision problems, okay? So this is two very important event. And in this slide, I show you some reasons why deep learning algorithm is operate better than the classical machine learning algorithms. So the first row is showing the classical machine learning pipeline, and the second row that is showing the deep learning algorithms pipeline. Okay, so as you see in the previous OpenCV practice, the input images are loaded in some variable, and they are represented as some array. Okay, so width by height by channel number sized array. Okay, so you have to read input images into the variable in the Python code, and they are represented as the array. Okay, with the 3 dimensions. So, anyways, input images are represented as the array. That's same for deep learning and machine learning algorithms. But in the machine learning algorithm, you have to extract some feature vector, which is the vector that efficiently captures some characteristics of the input images. So for example, when you want to solve the skin detection problem, the important feature vector might be the color. Okay? When you want to achieve the skin detection, color might be very important feature. Okay, so actually there are skin detection means you have to detect some skin here, right? Human's skin here, and maybe for solving that, the color is very important feature. Okay, but humans actually have to define which feature would be helpful for solving this problem. The humans by themselves have to define that, okay? And then after that, after defining and extracting the feature vector from the input images, we use some shallow layered algorithm, which is the classical machine learning algorithm, such as the SVM or linear regression algorithm, to map these features to output. So for example, in the skin detection problem, we have to classify each feature vector into skin or non-skin, okay? So the output might be non-skin or skin. Okay, are you agree with it? Okay. So I mean, this is the classical machine learning algorithms pipeline. But the problem here is, if you don't know, let's assume that you don't know the useful features for solving your own problem. Let's assume in that scenario. So for the skin detection, we can easily guess the color features might be a useful feature for skin detection. But for some unknown tasks, even humans cannot easily guess which features would be the, useful feature for solving that task. Okay, right? Is that right? Okay. So, defining feature vectors sometimes very hard because we humans even don't know the relationship between useful feature and the output tasks. And also we can mistakenly miss some useful feature vector for solving that specific tasks, okay? Or maybe we can, sometimes we inefficiently use additional features which is not that useful for solving some tasks, okay? So the problem lies in the fact that we humans have to define the feature and have to extract the feature by ourselves. That means we have to use human engineered feature, okay? So this part is having some inefficiency, okay? Anyways, uh, I mean, for example, in skin detection, color feature is very useful, but we mistakenly can miss that color feature, but instead use some other, which is not that helpful feature. In that case, we lose some very important information at this level already. So how good the shallow architectures are performed in the later stage, the accuracy for the skin detection problem or some other tasks might be bad. Okay, so there are some inefficiencies in the feature extraction part in classical machine learning pipeline. Okay, are you understanding that? Okay. But the thing in here, in the second row, I'm visualizing the deep learning method. And here, what they do is they directly map the input array to the output vectors. Okay. So for skin detection, the output might be non-skin or skin, but we directly estimate it from the input pixel values. Okay. So this is the merit of the deep architecture. So they don't involve inefficient, the human engineered feature extraction part. And also, actually, this is the summary for why deep learning performs better. I mean, if you say these two others, when they ask you why deep learning performs better than the machine learning, classical machine learning, then answering these two might be close to the ground truth. Okay, I mean, um, for machine learning algorithm, we need to design dedicated representation by ourselves for each task. Okay, so I mean, this feature extraction is human engineered, so we can miss sometimes, or we can overuse some unnecessary features. Okay, so there are some inefficiencies in this feature extraction part, but deep learning learns intermediate representations automatically for different tasks. So it is known that in deep learning, the first part of the deep architectures tend to learn the features, and the later part they are ruled as the classical shallow architectures that classify the features. So inside these deep architectures, they are automatically do something they are learned to do something, okay, based on the data. So, they are becoming more optimal compared to the classical machine learning algorithms, okay? So this is what they are saying. And the other thing you have to answer for why deep learning performs better than previous machine learning approaches is you have to understand the non-linearity, okay? Non-linearity is opposite term for the linearity, okay? What linearity means, let's say there are two types of data samples like this. This symbols X and O is denoting different labels, okay? And also if you are some other people say you to classify these two data, then you may with the straight line, then you may say this kind of straight line, okay? So this straight line can classify these two different symbols. Is that true? Right? So this linear case means if you draw one straight line and to divide two different classes, then that is called as the linear case, okay? But this is the linear case. But in this kind of situation, you can think of, in this situation, you cannot draw just one single straight line to divide these two symbols, okay? This case is called as nonlinear case, okay? You cannot draw just one single line to completely divide these two symbols, okay? This is the nonlinear case, and in this situation, you need this type of nonlinear boundaries to maybe classify these two symbols, okay? So you, in the high school, you may learn these straight lines are represented by this simple equation, okay? So straight line, they are called as linear equations. But you also learn that if you increase the power here, for example, as 2, then it becomes like this, having some curve, right? It is no more straight, but have some curve, okay? So, and it is also can be said as nonlinear. So if this power increases, it means the function becomes more complex, and it means it becomes nonlinear, okay? It is having curve, and it is not anymore linear equation, right? Are you guys understanding this? Okay, so in this simple case, in this simple linear case, we need just one linear boundary for classifying these two different symbols, okay? But in this complex situation, we need some nonlinear boundaries, having some curve, okay? But thing is, the shallow learning algorithms, this kind of shallow learning algorithms, their functions are mostly like this, represented like this, and they are linear equations. Okay? If the layers are shallow, we can only represent some linear mappings between input and output. Okay, but if we stack multiple linear layers, if we make it the algorithm's architecture deep, we can gradually represent the non-linearity. Okay, so this is important sentence. Deep learning can represent the non-linear mappings between input and output. Okay, so deep learning can solve this kind of more complex data distribution. But shallow learning algorithms can only properly deal with this kind of linear case. Okay, so getting deeper architectures can represent this kind of more complex non-linear data distribution, but most of real-world data are lying in this non-linear distribution. Okay, so that's another reason, important reason why deep learning performs better than classical shallow learning algorithms. Okay. So if you are asked by some other person why deep learning performs better than classical machine learning, then you can say these two. Deep learning can learn some optimal representation from the data. Okay, it no more involves the hand-engineered representation, and also if we are making the architectures deeper, then it can better represent the non-linear data. Okay, and most of the data in the real world, they are in the non-linear distribution. So the deep learning performs better than classical machine learning algorithm. Okay, that's the best answer maybe. And I want to also say this. Any questions? Any questions? No? Okay. And also I want to introduce this convolutional neural network. This is the convolutional neural network. Okay. This is called as the CNN. And actually, this is very famous deep learning architecture. So, I mean, here, AlexNet, I said AlexNet has appeared here. And it is one of the CNN algorithm. Okay. They are called as CNN because they are mainly used the convolution operation. Okay. Have you heard about the convolution operation before? No, none. Is there anyone who already takes signal processing course? No. So, anyways, signal processing, that's the double is course. Signal processing. So here they learn about the convolution actually operation, but you don't have to worry about that. This is very simple operation actually. Roughly, convolution, I already show you here I already show you how to blur the images. Okay. So here, you saw we can blur the original images, right? Have you heard about the expression like applying some filter color on the image? Have you heard about that? Okay, maybe when using the Photoshop, you may heard about that. So when transforming the original image to others, we normally, in our daily lives, we normally say applying some filter to the images. Okay. Actually, this is the files are deleted, so this is no more working. But anyways, this blurring is one example of applying filter corner on the image. Okay, so if you use this type of filter corner on the image, what they do is this is, let's say this is the image. This is the filter corner. What they do is they apply filter, they locate filter here and element wisely multiply that filter corner values, which is actually one, and also the pixel values inside that window. Okay, and then they add them all to generate one output pixel value in output image. And they move this filter corner by 1 pixels right and do same thing to obtain this second pixel output. And they actually do this in this zigzag manner and make the output images here. Okay. And if the filter corners are like this, having all one, then the output images will be the will have the pixel value that averages pixel value with nearest neighbors. Okay, are you guys can imagine that? Okay, so when you obtain whole image output here, they are blurred. They are averaged with nearest pixels, so their images are getting blurred. And I already showed you that if we change these values larger, then it is more blurred. Because these parameters are meaning how many we average with nearest neighbors. If we average 1 pixel with large amount of nearest pixels, they are more blurred. Okay. And if we average them with fewer pixels, then it is not that blurred. Okay. So I will show you that again, maybe. I'm not sure. Maybe I can. Okay. But anyways, if you change this value to 1, it is not anymore blurred because it is same as keeping the original value, only. So this have to be larger than maybe 1 to, average with more than 1 nearest value, okay? If it is just a 1 by 1, then, it is meaning not average with nearest pixels, so it is same as the original values, okay? Anyways, the thing I want to tell is this kind of thing, this kind of operation, applying some filter color on the image, that operation is actually convolution. Okay, so applying filter that you usually say is same as performing 2D convolution operation with some filter color. Okay. Are you guys understanding this? Okay. And also you have to notice that in this is actually the 2D convolution operation. And in here, what they do is actually element wisely multiply the pixel and filter coefficients and add them. Okay, so actually the output value is calculated via this multiplication and addition of the input variables. Okay, that's the convolution operation. Anyways, the CNN is using this convolution operation as the main operation because previously, when transforming the images into to have the different characteristics, we normally use the convolution operation. Okay. By changing these filter kernel values, we can transform the images to have different characteristics. Okay. So actually, this convolution is good way of transforming the input signal to different domains. So this convolution neural network, they are involving this convolution operation because they are frequently used image transforming method. Okay, so they are, good at transforming the image characteristics. That's the first reason. And second reason is they are composed of only plus and multiplication and addition. So their output is differentiable respect to the input and also the filter kernel. So every polynomials are differentiable. You guys already know that maybe. So if the function is like this, so this function is differentiable with respect to x variable, right? Every polynomial is differentiable to their input, okay? Because they are composed of multiplication, addition, subtraction, and division. If one function is composed of these 4 operations to make output, when making the output, their input variables are operated using these 4 types of operations. That function is actually differentiable to the input and differentiable to the intermediate variables. Okay, this is actually very important characteristics when constituting the deep learning algorithm. Maybe I will explain why maybe in the next class. Okay, maybe but before finishing, I want to say this. So CNN is one representative algorithm in deep learning. Okay. So deep learning means if you stack multiple layers, then that algorithm is called as deep learning algorithm. And CNN is one branch, one example, representative algorithm in deep learning. Because they stack multiple layers, but their layers are actually the convolutional layers. Okay, you can stack multiple layers, which is differentiable. Okay, any differentiable layers can be here between input image and the semantic maybe classes we want to achieve. So we are assuming that we are solving the image classification task, but we can even though we deal with the different tasks, anyways, there are some proper output. We can map the input images towards the proper output using any differentiable layers. Okay. But I mean, the convolutions are differentiable operation. So the deep learning researchers are thinking about stacking the convolution operation for dealing with this kind of image classification task. Image classification task. And also the convolution, another reason is they are dealing with image classification task, which is using the input images, not text or not speech. And also the convolution was the useful operation that can efficiently transforming the images. So they try to use convolution operation inside the deep learning architecture. And in experiments, they found that that actually works very well. Okay. So in the year of 2012, here, they constitute the deep learning architecture using convolution operation and found that that works very well. Okay. So in practice, the CNN works well. So we are actually using that nowadays. Okay. But I mean, there's no proof that convolution is the best operation for mapping this RGB input and also some class output. But in practice, we are using that because it performs very good. Okay. And maybe from next class, I will show you why the differentiability is important in deep learning. Okay. And also we'll show you how to calculate how to actually training the deep learning architectures. And also we'll review actually the exact operations inside the convolution layers and also exemplify the big architectures, the actual architectures the CNN, exact architectures in CNNs. I think the slides are a bit different. Anyways, okay. So from next class, I will explain this part again. Okay. Thank you, and see you next Monday. Okay. Thanks. So if you have any questions, please ask me maybe after class. Okay.